Going to do 11.9 today. That's definitely going to happen, and we'll see how far we get after that. Essentially, we are going to take guys like this and find out what the power series is. And the only really things we have to work with is the fact that this fraction has this power series and this fraction has this power series. So how are we going to get these guys power series using that? Some algebra and definitely some substitution. So I'm just going to jump right in because I've got my little list. Here's the guy. Let's figure out whose power series is. Right, when I look at this guy and I compare him against these two, would you agree it looks more like, I don't know, I'll call this guy A, and right, I'll call this guy B. And do you think we agree it looks much more like A than it does B? And then I look at this and I look at this and I say, if I could substitute the x for an x squared, we would be good to go. So what I'm going to do is I'm going to take this fella and substitute him for x squared. Now, unfortunately, a lot of students think that's finished because, you know, there's your power series. Well, you're meant to tidy power series up. They have a kind of their own rules of style points. And the biggest rule, apart from the obvious one of if you can cancel things and simplify them, you should. The biggest rule is that x has to be written as a power on its own. So it can't be written as x squared raised to the n. You have to call it x to the 2n. That's a pretty easy one. A lot of these questions are going to say, and find the interval and radius of convergence. We did that yesterday, right? Ratio test, usual way. There's probably a good chance, just looking at that one, that the answer is going to be -1 to 1. It's my gut feeling. But that part I'm not going to do. Okay, second guy. Well, it could be A, could be B. Would you agree it's closer to being B because of the plus? Problem with this guy, I can't do substitution yet. And the reason I can't do substitution is that 8 isn't a 1. This second term can be anything. It can be x squared, it can be the square root of x, it can be anything you like, but it's not a problem. But this must be 1. So I'm looking at this and I'm going to have to figure out a kind of weird way to fix that. Would you agree that if I tried to pull out 8 as a common factor, I'd get this? Agreed? So I'm only going to focus on this guy, right? In fact, maybe if I write it down, it's two separate things that may stand out a little bit better. So I am going to find the power series of this guy. Well, if you look at this one and you look at this one, isn't the substitution going to be 1/8 to the power 1/8 of x? So we have 1/8 sigma n equals 0 to infinity, and replace the x, that's the guy that goes here, by 1/8 x. Now for the next few lines, all I'm going to do is make this look pretty. Can I take this 1/8 and bring it inside the sigma? Is that allowed? Right, so I'll do that. Do you know this fella here can be written as that fella? Can you imagine it being x over 8 raised to the power of n? Now, almost finished. See, this guy and this guy can come together. And there you are. The power series for this fraction is him. We cool? This isn't really a new question. This is an adaptation. Suppose I wanted to do the power series of x cubed over 8 plus x. If I already know what 1 over 8 plus x is, isn't this just x cubed times that? This already represents this piece. Isn't this essentially x cubed times that? That means I can call it x cubed times this power series. Would that be the finish, or can we make it prettier?
Make it prettier.
Right. If you take that x cubed and you bring it inside, don't you just add 3 more to the power? So I don't have to redo it and I'm running short of room. We cool with it? Right. So sometimes it's a good idea to maybe, rather than eat your meal in one go, in other words, try to fix that in one big process where you might lose track of what you're trying to do. And maybe you should break it into smaller chunks. Right. Figure out what that is. That's the hardest part. And then just add on 3 later. So that would be a little bit easier to keep track of. Any questions about those two so far? Okay. Same, essentially the same vein, but just a little tweak. And this is my question 3. This guy doesn't look like that guy. But he's in the family of them, right? He's in the same family. It's not exactly the same. There's a 4 on the top, which we can deal with very easily. And we got a 3 in the bottom, which isn't so nice. Now, I'm not saying that you would necessarily do it as methodical as I'm doing it. But the first thing I would probably do is to think of it as that. Now, just take the 4 out of the way for a little while so it's not interfering with me. That 3 is a problem, isn't it? Like the previous question. So what I would then do is something like that. I'm going to suck that 3 out. So this guy gets transformed into this guy. Now, once he's written like that, can't I go to this one here and do a substitution where I'm going to replace the 1/3 x, right, here. Right, substitute that 1/3 x right in here. So that means I'm going to get 4/3 sigma n equals 0 to infinity 1/3 x to the n. Going to bring in the 4/3, and this guy is going to be called x to the n 3 to the n, and then make it as pretty as you can. We're finished. So the power series of this rational function would be this guy here. And then you could go and do its interval and radius of convergence or whatever else it asks you to do. You see, with a clever bit of algebra manipulation, it's possible to take a lot of rational functions and create their power series when the only two power series that you know for sure are these two building block ones. And it's just a matter of how to make this guy more compatible with whatever one of these two you end up going with. Okay. Next one is this fella. A or B? Who do you think that one's? What family is he a member of? Is he in family A or is he in family B? Should be pretty easy to tell.
B.
Right. Now I know that B has to look like this, right? And the only thing I can really have that's different is, can't this X be other things? Can this X be a third X? X cubed, you know, a half X squared, right? This is really the only bit that can be different. And I've got a lot of different, right? Now, I'm going to call that X. I'm going to pull out the 9, and now it's going to be called that guy. And I'm going to pull out those two terms so that I can separate out the guy that I need. You see, that guy is usable with him. That's my whole goal. To take what I've got and write it down so I can use, in this case, B. That's going to get me X over 9. And then I just do substitution. And in this case, I'm going to substitute that X with a 9th X squared. Oops, too late. Right, you want to break this power down. Would you agree that it's 9 to the n on the bottom? What about x squared raised to the power of n? What power of x does that become?
Wouldn't it be x to the third plus n, or x to the n plus 3? Oh, I thought we were, I'm sorry, I'm a step. Yeah.
Okay.
X squared plus n.
Is it plus n or 2n?
Oh, it's 2n.
Right. And I'm not going to write this down, but I'm going to do it. Can you imagine that x coming inside and that 9 coming inside? And what would happen in that case is that you'd get another guy, which might be what you were thinking about a few minutes ago, a few things ago, and that guy. We're cool? There is a process to this, isn't there? At least the ones we've done. There is an algebra thing. It's a bit, oh, I don't know, a bit intense at times. But I mean, it does have a flow to it. You take the guy and you try and rearrange it so that it has a thing that looks like this. There must be a 1 on the top, there must be a 1 here, and then you can have anything you like next. We don't care what that is, that's okay. You can have it. If you can get it to that shape, want to be A or B. So then you substitute. And then you take care of the little bits that you had to take care of to make it work and bring them back inside. Next fella. I'm going to change tack here. This would be my question 5. Suppose I asked you for that guy. You should be saying, hey, that's easy. Isn't that just this guy with the x replaced with x squared? And you are right. If you thought that, you are right. N equals 0 to infinity, -1 to the n, x squared to the n, right? Replace the x with x squared. Tidying this one up isn't much of a chore either. And if that had been the question, that would be a 2-liner and you'd say that was an easy one. But that wasn't the question. The question is actually, Find the power series for the inverse tan of x. But to find the power series for the inverse tan of x, I needed to know the power series of this guy, because I'm going to do something to this guy that's going to get me that guy. What could you do to this guy that would make him that guy? Not that direction, but this direction, right? Going this way. What do you do to this guy here that would give
integrate.
you integrate? So I'm going to find the integral of that guy. And we know that that guy is what, tan x plus c, right? Inverse tan of x, right? Well, that means I'm going to integrate its power series. And one of the really cool things, and there's many cool things about power series, but one of the really cool things about a power series is that you can integrate it. And the integration and the summation symbols or processes are interchangeable. In other words, you can switch them, which means I can now do n equals 0 to infinity of the integral of that guy. So summations and integration can be switched to integration summation and vice versa. If I put a little, I don't know, bracket around that just for emphasis. Isn't that basically just x squared, x to the 4, x to the 42, with some funny little negative 1 to the n? Isn't the rule for powers of x called the power rule? And it says you add 1 to the power and then you divide by the new power. So if I want to integrate this, don't I add 1 to the power and then I divide by the new power? Great. So far, so good. Right. Plus a really annoying arbitrary constant called c. Okay. Now, I need to know what c is. And sometimes you're going to get the answer and you find out c is really weird. It's like the inverse tan of 1. I think there's going to be a log question where the plus c ends up being the log of 4. Whatever it is, you just tag it on at the end and call it good. But I need to know how to find c. And the typical way to find c is just to make x equals 0. If this is true for every value of x, that means it's true when x is 0. Right? And the inverse tan of 0 is 0. Do you know all these guys here are going to be 0? 0 equals 0 plus c. Oh, c ends up being 0. If you were programming the TI-84 calculator to evaluate inverse tans, how do you think they do it? Pretty sure I know how. They use power series. One of the lovely properties about power series is that the value of the function, although this is an infinite series, 99.99% of what the thing is contained in the first few terms. So all you really need to do is maybe write down the first 6 terms. It'll be a polynomial. And you can take that polynomial and it will look and behave and have values to like 8 decimal places at least, the same thing as the inverse tan of x. So all you basically do is you store polynomial approximations to every function that you ever would have, e to the x, sine x, cosine x, inverse tan of x, don't care. Every single one is a power series. And every single one, essentially, if you use the first 5 or 6 terms, you got the answer to as many decimal places as you want. Way back in the days before calculators, and yes, mathematicians did exist then, when they had to do calculations like inverse tan of something, they had books called tables of values, and they would just look up the inverse tan book, and they would have, 1, 2, 3, 4, 5, 0.1, 0.2, 0.3, 0.4, and they just read down, and they'd have a decimal answer, and they would just write it down. And that's how they had to do their computations. That poor table was created by what would be the equivalent of clerics who were just given jobs of, here is a polynomial, here is 1.2, get the answer. And they would give it to 2, if they were sensible, they'd give it to 3, but they would normally give it to at least 2 people independently. And they would get the answers. And if the answers agreed, it gets stuck in the table. And if the answers didn't agree, then they assumed that someone or other screwed up and they would redo it. And that was the equivalent of error checking that you might have done on a computer. Yes, Travis?
I actually remember hearing that calculator used to be a job title and not an object, because people used to actually have to do all the calculations.
Yes.
You'd have to admit them in the morning, and you get them back at the end of the day.
Yeah, it's a bit like my card thing. You'd say, I need to know these things. And the guy would, if he didn't have a table with all the ones, I guess the sensible way is you just had a table of values. But if for some reason it needed to be more, can you imagine you just had a big polynomial where you had to do 1.23 cubed divided by 5, added to 1.23 to power of 4, so on and so forth. God, that job would drive you crazy.
I feel sick just thinking about it.
Yeah. And what did you say they were called again? Calculators?
Yeah, that was the job title, calculator.
Good. Do you know when it stopped? When did they actually, it probably was, I'm guessing 50, 60 years ago, because before then there wasn't really much to work with.
I believe they did through Apollo. I could be wrong.
Wow. Go figure. Right. Interesting information. Right. So I just did 1 over, oops, sorry. That's the inverse tan of x, right? So you do that one. That one's called 5, so this is 5 star. Suppose I wanted x cubed, inverse tan of x squared. What you would do is you would use the previous result. Hopefully you had to remember that you did it, and you'd go and look it up and you'd find it, and you'd use this guy. Because won't I now be able to use this guy with him? And won't this be a substitution? So the inverse tan of x squared will simply just be what you get when you replace the x with x squared. And what about the x cubed? Tag it on at the side. Then you can figure out this guy. X squared raised to that, 2 times 2 times, you get 4n plus 2 over 2n plus 1. Bring in the cube, which essentially just adds on 3 more to the power of x. 3 more gets you that guy. Boom. It's almost like a little avalanche, isn't it? It started off with two little snowballs, right? Two little pieces of information that we have, and then from these two pieces of information, we could basically get, couldn't we, a lot of different rational functions out of it. And from these two pieces of information, with a little bit extra work, we ended up getting a power series for an inverse tan. And once we got that, couldn't we then get a power series for a function that contains the inverse tan? You can see it can kind of just grow and grow and grow. And you can do all sorts of,
Quick question in regards to this.
Mm-hmm.
So we had a new power that ended up going to 4n plus 5. Why did we not move that down to the bottom?
What, the 5? I'm not sure what you want to move to the bottom.
So we have 4n plus 5 up top, but we
Yeah.
retain the 2n plus 1 on the bottom. I thought that the power series was divide by the new power.
Divide by the new power. Oh, I haven't integrated this.
Okay.
I mean, this is just pure substitution. There's no integration happening here. The first one here, right, that was divide by the new power, right? Because what I did here is I integrated the power series and thought, I'm doing that. And this one is using that guy as a building block. So it's just pure substitution. So that process here is not integration, it's substitution.
All right. Thank you for clarifying.
Okay. So actually, I've called that 5, but it's really my question 6. Right, here's one where you don't have clues. Question says, find the power series for that log. So we need something to work with here.
It's the integral of 1 over 1, negative 1/2 over 1 minus 2x.
Yeah, essentially. If you integrate that, just the way it is, can you see that what you'll get is the natural log of 1 minus 2x, but you'll get a really annoying negative 1/2. Agreed? Now, since I only want this, couldn't I get the answer by just having negative 2 times this fella? So we have got the method that we're going to use to find the power series of this log. It's going to be essentially that integral with a little multiple here just to make everything, balance out. Well, now I've got this. My quest is going to start off by finding the power series of that. Then I will integrate it, and then I'll stick a minus 2 times it when I'm finished. Right, who does this belong to, A or B? Which power series does this belong to, A or B?
A.
A. What will be the substitution? What will I replace this x by to make this happen?
2x.
Comfortable where that came from? Now that becomes that guy. Right, now let's always keep in mind where we're heading. We're heading to here. Well, I got this bit, right? Want to now integrate this bit. Which means that I can integrate this fella. But I also have a negative 2. So can I just stick the negative 2 on the outside worry about it at the end. So we have a -2, we have a sigma, n equals 0 to infinity, and we'll just integrate that guy. So this is the power rule of integration coming up. You add 1 to the power, and you divide by the new power. And you have that annoying plus c to deal with. If I bring in this -2 to this, do you know I just get a single random negative? Nobody. Yeah, we're good. I was going to say nobody caught it, but I think I caught it. Are we good so far? That means I now have this guy. The power series for this guy is this ugly thing. Excuse me.
Bless you.
It's this fella. We have to find C. We're not finished till we do that. Don't we just plug 0 in and see what it gets? If you plug in 0 here, don't you get the natural log of 1, which is 0? If you plug in 0 here, can you just imagine these all kill each other off and you get nothing? So it ends up C is 0. And that's nice, because it means we now have a really big, quite ugly power series. Okay. I'm going to do a kind of step back. We've already found this power series, the inverse tan one. If you write this out, let's do, I don't know, let's do the first 4 terms. You plug 0 in, you plug 1 in, you plug 2 in, you plug 3, right? Or whatever we got. You plug in 0, you'll get -1 to the 0, x over 2 lots of 0 plus 1 over 1. And if you do the next one, you're going to get -1 to the 1, x cubed over 3. If you do the next one, you're going to get -1 squared. What was the next one? 5 over nothing, 1, 2 over 5. And if you do the next one, that's the last one I want to do, and you get this guy, you get 7 over 7. Let's make it pretty. That's 1, so you basically get x, and that's -1, so you get what? 1/3 x cubed. That's +1/5. And this is -1/7. Actually, when you see it that way, doesn't the inverse tan function have quite an elegant polynomial look to it? It's not actually that random, doesn't it have a kind of oddness about it? If I kept on going to infinity, which I won't, but if I kept on going to infinity, wouldn't every power of x be an odd power of x? Could you remember that functions, some functions at least, were called odd and others were called even? And it seemed like a strange name, because odd functions had the property that if you turned them upside down, right, they had rotational symmetry. And even functions had the property if you reflected them on the y-axis. And it was kind of strange that, for instance, cosine x is an even function and sine x is an odd function. And you might think, why those names came about. Well, here is the secret. They came about because of their power series. Do you know the inverse tan of x is an odd function? If I did, and you will eventually get to see this, if you do cosine x and you find its power series, which it is possible to do, you will find that it is made up of even powers of x. It's got x squareds and x to the 4 and x to the 6s and all sorts of cool stuff like that. Isn't that interesting? Now, I am going to find the inverse tan of 0.1. And I'm going to get the inverse tan of 0.1 from my calculator. So I'm going to make sure that the mode is in radians, which it is. And I'm just going to go inverse tan of 0.1. And the answer that I get is 0.09966865525. You agree that's pretty good accuracy, right? Now, if I only use those 4 guys, I can say that the inverse tan of x is approximately equal to this polynomial. Then shouldn't that mean that the inverse tan of 0.1 is approximately 0.1 take away 1/3 of 0.1 cubed plus 1/5 of 0.1 to the 5 take away 1/7 of 0.1 to the 7. Right, I am now going to do that calculation. Hopefully I won't screw up. How impressed would you be that this polynomial, which really only consists of 4 terms, right? It's only got 4 bits to it. How impressed would you be? Would you be impressed if it was good to 3 decimal places? Would that impress you? Would you need maybe 5 decimal places? How good is it? Let's find out. 0.1, subtract 1/3, which I'm just writing that funny way, times 0.1 cubed, add 1/5 times 0.1 to the power of 5, subtract 1/7 times 0.1 to the power of 7. And the answer I get is 0.099686524. That's pretty good, isn't it? Do you see how powerful power series are? Probably that's why they got the name. I'm making this up. That's probably why they're called power series. Can you see how powerful they are? How you can take a function like the inverse tan function and express it in terms of a polynomial that only has 4 terms, and yet we're getting answers that are good to 7 or 8 decimal places. And if that doesn't impress you, nothing will. That is just phenomenal that we, not me personally, but mathematicians even came up with the idea of power series. I mean, try and imagine nobody had thought of power series, right? Nobody had thought that a function could be written down as an infinite polynomial, right? That concept just hadn't came into anybody's head. Can you imagine how mind-blowing it was when the first person, finally the light bulb went on and they started doing this? And I'd say, wow. I'll show you one last thing. I'm going to go into y equals, and I'm going to do the inverse tan of x. And this is going to take me a little bit of time, so you're going to have to hopefully be patient. There's x, take away 1/3 x cubed plus 1/5 x to the 5 subtract 1/7 x to the power 7. So I'm going to be showing you a sketch of the inverse tan of x and this polynomial, right? This 7th degree polynomial. I'm going to choose my own window. So I'm just going to do it from 0.3 to positive 0.3, right? And I'm going to do zoom 0. Actually, my window's probably not as good as it could be. Do you see that little thing at the right-hand side that's going up and down? Oh, it stopped. Oh, there is only one graph there. It's very linear looking. There's only one graph there. What is that? Do you know that those two are so like each other that for all intents and purposes, isn't it the same graph? Okay, open the window up. Maybe I can get a difference. How about -1 to 1? So I'm going to do the same inverse tan. This time it's going to be from x is -1 to 1. So there's the inverse tan. Can you see the inverse tan beginning to curve here? Now, if you look really carefully, do you see at the end, there's a little bit out? And do you see at the other end, it's a little bit out? Do you see it beginning to separate? Right, one last one. Suppose I do -2 to 2. Oops, sorry. Let me do that again. Oh, it is okay. It is okay. Do you see that at the ends now, it really gets quite bad? So somewhere round about -1 to 1, this approximation starts losing its accuracy. And the reason it loses its accuracy is that all power series are really, really good close to the center. The center is 0. So 0.1 is great, right? 0.2 is not so good. 0.5 not so good. 0.9 not so good. But eventually, they will dissipate. To me, that is amazing. I can look at a power series and I'll tell you if it's odd or even or neither. I can use the first 4 or so terms, and very often I can get the value of that function to as many decimal places as probably my calculator. And that's just with a polynomial with 4 pieces. Okay, question 8 now. We're being asked to do something a little bit different. This guy. Right, my answer is going to go here, but I need a starting point. That's basically my starting point. Agreed? Who does it belong to, A or B?
A.
Agreed? Would you agree here that the substitution is going to be t to the 4? So we're going to get a t times sigma n equals 0 to infinity t to the 4 raised to the power of n. And that's going to be n equals 0 to infinity t to the 4n. And can't I bring this guy inside and get 4n plus 1? So this integral becomes the integral of this guy. Of course, thought ahead, I would have brought this down a little bit. So can't you switch sigmas and integrals around? So it's going to be sigma n equals 0 to infinity, the integral of t to the 4n plus 1 dt. Power rule. Add 1 to the power, divide by that new power, and then tag on a c. But in this question, it's okay to have a c because it's an arbitrary constant, and that's what you would typically get. Do you see that what we now have the ability to do is, can't we now find integrals to things that we couldn't find in the past? If I asked you to do an integral of this guy, actually, I think this one's maybe possible, but in many cases it's not. Isn't there lots of integrals you can't get the answer to? 1 over 1 plus x cubed. Agree that's dead. That's going nowhere. But you still want to know what it is, don't you? Well, if you can find its power series, can't you just plug in, maybe use the first 4 terms like I did with inverse tan? Can't you plug in the start value and the finish value, do a quick subtraction? Won't you be able to find its integral to any, any degree of accuracy you felt like? If you don't like 4 terms, hey, give it to a computer. Tell it to use 4 million terms. Right? Well, that would take me my lifetime, and beyond. But for a computer, can't it do 4 million calculations like it was nothing? 2 seconds or whatever. So we now have the ability to integrate numerically, right? Get a numerical answer to anything in the world that we want to integrate, to any accuracy that we want. Pretty powerful. Okay, we're getting to the tail end here. There's this question. Yes, Travis.
Is it true that like most expressions can't be integrated and you would actually have to use a power series for them or something?
Yeah, or some numerical technique like Simpson's rule. Yeah. Yeah. There's an infinite number of them. It's kind of hard to talk about how many there are when both answers are infinite. There's an infinite number of functions I can find integral to. I mean, if you want to just be silly, can't I find integral to x, x squared, x cubed, x to the 4, and just keep going, right? There's an infinite number. And there's an infinite number of things that I can't find integral to. So I'm not sure if it's possible to answer that question the way it was phrased. Are there more things that you can't integrate than you can? Because since they're both infinite, it's kind of hard to compare them, right? How about there's a lot of them, right? Let's just be vague. There are many, many functions that can't be integrated. The chances are that if you just randomly wrote down some stuff, x cubed e to the x or something, right? If you randomly wrote down some stuff, I think you'd probably end up writing more situations that you couldn't integrate than those that you could. So if that was the way I was testing it, yeah, there are more ways, there are more functions out there that you can't integrate than there are that you can. Right. This guy's a stinker, right? The next question is going to be a lot easier than this one, but this one's a stinker. Because we have to do a lot of groundwork before we even get to integrate that. So try and leave some space this time. Don't we need to find the power series for that guy before we can integrate it? But wait a minute. Don't we need to find the power series of that guy then? And then multiply it by x squared? But to get that guy, won't we have to find the power series of this guy? Do you see it's a kind of chain reaction? Okay, if I find the power series of this guy, how's it going to help me get that guy? Well, this guy is easy because we know this guy. I don't really need to do a lot of work. How am I going to get the power series of this guy? Using that fella. I know this. How am I going to get the power? Say again?
Integrate it.
Right. I'm going to cut some corners here because I don't have a lot of space. Don't I just integrate this power series? And when you integrate the power series, essentially, don't you add 1 to the power and divide by the new power? Technically, there'd be a plus C. Can you trust me it's plus 0? In which case it's gone. So if I want this guy, don't I just take this answer and multiply it by x squared? And what that gives me is that guy.
Mr. Robertson,
Yes.
it should be -1 to the nth power for the bottom. You forgot.
Oh, thank you, thank you. The good news is that that's easy fixed. Well cut, thank you. So we get this guy with that little scribble meaning -1. So this fella now becomes the integral of the power series of that, which is this. So it's -1 to n, which I forgot, but it's fixed. We have an n plus 3. And the whole thing is going to be over n plus 1. And then we'll switch places and just integrate. Okay, that doesn't really matter. That's like 5, so that stays put. If you integrate a power, don't you add 1 to the power and divide by the new power? So if you add 1 to the power, you now get n plus 4, and you divide by that new power, means that you now have 2 distinct guys at the bottom, plus C. So to get that guy, I started with this fella. This fella then allowed me to get that guy. That guy allowed me to get that guy. And once I got this guy, I could then go up here and actually do what I needed to do, which was integrate. Do you see it's a kind of deconstruction process, isn't it? You know what you've got, but you got to figure out, breaking it apart, what you need to get first that will allow you to get this guy second, which might allow you to get this guy third, which finally gets you the question you're being asked for. And that deconstruction process is the part that can make people a little bit wary, because you don't get an awful lot of practice at anything. But now that you've seen that set up, does that seem like a logical progression of what you need to do to get that particular integral? We are cool. I'm just going to move this guy over there because I know some of you are writing, and we'll do the last question, and then we can get started on our second last section. That's how close we are. There's a little kicker in the tail here. Oh. Why does this particular power series, which I'm calling f of x, why does this one have to start at 1 instead of 0?
Because if it started at 0, it'd be 0 over 0, or 0 over 1.
Yeah, x is 0 over 0 and not good news, right? most power series start at 0. Some of them start at 1. That's the main reason. Very often, n equals 1 doesn't work. You know, the power series, you know, has bad values, typically 0 on the bottom. I've seen some that had to start at 2 for that same reason. You know, 0 and 1 don't cut it, right? You have to start a little bit higher. Yeah. So far, so good. Now, wouldn't it be nice if you could differentiate power series? We know how to integrate it. Wouldn't it be nice if we could differentiate? If the world was fair and everything that you wanted to be true was true, what would be the easiest process for differentiating this power series?
Power rule.
Right. Wouldn't you just differentiate the individual pieces? Isn't that what you do when you integrate? And the answer is yes. If you differentiate this, don't you multiply by the power, and then you reduce the power by 1, and I get this guy, right? Oh, this is interesting. Can I get a little cancelling? Suppose I wanted to get the second derivative, and I wanted the answer as a power rule. Sorry, I gave the answer. I wanted the answer. Wouldn't I just use the power rule? Multiply by the power and reduce the power by 1. Comfy? Everybody happy? One last time. Multiply by the power and reduce the power by 1. Everything looks totally fine, doesn't it? Plug 1 into that. Right? Plug 1 into that. These terms here, actually, I think one of them 0, but pretend that didn't happen. When you have a problem with the power of x, wouldn't it be -1? Can you imagine that term there wasn't 0? What in the heck is going on here? What happens when you differentiate a function and the first term is a number like 5? What happens to it? Doesn't it become 0 and disappear? And if you do a second derivative, won't the term that used to start off as 4x became 4 and now will disappear? Do you see that you actually eat up or use the first term each time you differentiate? And because of that, the starting value should move up 1 place. Now, in this particular question, the powers were what's the word I'm saying? The powers were safe because they were so big. But in general, be on the lookout for terms that don't make sense. Now, in this case here, I could have got away with 1 and 2. In this particular question here, I could have got away with it because this one was 3. But if I did enough derivatives, can you imagine there comes a point in time where I should have actually started at a different number than 1, because at 1 you would end up generating negative power of x. It's really cosmetic. If you don't even notice it, you probably won't get into trouble, because it's one of those 99 times out of 100, everything goes fine and you don't need to worry about it. But you are not allowed power series with negative powers of x, and therefore you should add 1 to the start value. And that is the end of 11.9. Any questions before I move on to 11.10 then?
So is it just good general practice to add 1 to the starting point?
Is
Is it
it's
better
safer.
to evaluate it when you're
Yeah.
going along?
Yeah, just have a quick look. If you need it, give it 1. You know, if you know n equals 1 is going to cause problems, then start at n equals 2. That would be my advice. If it ain't causing a problem, then just leave it alone. The vast majority of the time, it's not going to cause you a problem, right? Because you don't really get many derivative questions, and when you do, it's normally first derivatives. And you know, if you do a first derivative, you're probably, I'm saying probably, I know there's exceptions, you're probably going to be safe, right? I think if you move up, eventually if you differentiate something enough times, isn't there a chance one of them's going to go weird on you? And so it's just a warning to be aware that that could be an issue. I think the only question that they've got that looks like that in the homework wasn't an issue. So we are moving on to section, oh, was that the only question? The 11.9 gave us some sneaky algebra tricks, essentially. Using these two power series and a lot of tricks and integrating and differentiating and substitutions to get power series for lots of functions. But it has limitations. Suppose I would like to get the power series for e to the x. I couldn't use 11.9 to do it. Would you agree there's not a fraction in the world, right, a rational function in the world, that you could integrate or differentiate that would get you e to the x? There's not a substitution that you could do in a rational function that would do that. So we're kind of stuck. So a guy called Simpson, who I believe is Scottish, as all good mathematicians should be, didn't go to my university, unfortunately, but never mind. And another guy called Maclaurin figured out a way of doing this. And, well, I should say Simpsons. I should say, I take that back. The guy's called Taylor, not Simpson. And Taylor, I believe, is English. That's probably why my brain refused to remember it. And Maclaurin. And those two guys came up with a technique for finding power series of any general function you want. Right? You want a power series for sine x? Here's how you do it. You want the power series for e to the x? This is how you do it. And you will discover by tomorrow anyway, hopefully partly today as well, the power series for most of the common functions. To me, common functions are e to the x, sine x, cosine x, inverse tan x, which we already know, log of 1 plus x, things like that, right? Pretty standard common functions that you'll have met in trig or wherever. And we're going to find a power series. That's going to be pretty cool. So let's start off with Maclaurin's series. Useful or useless piece of information. He did go to my university, Glasgow University, but he didn't get trained there, and he wasn't a permanent member, but he did visit and he did do lectures there. Interesting thing about this guy. Do you know how we have things called child proteges? You know, there'll be some South Korean kid at 10 is going to university, you know, the kind of thing. Much, much rarer in the past. You know, when you were a 10-year-old in the past, nobody was expected to be a child prodigy. It wasn't even a concept, but he was one.
Wasn't 10 years old like when people were having their midlife crisis back in the day?
Well, if you lived that long, I guess. But typically, you wouldn't get educated at a university to the degree that he was educated at that time. He was, I'll get the dates wrong, but it doesn't matter. He was like 14 when he went to university. And I think he went through all the courses in 2 years instead of the typical 4. So he got his first degree when he was 16, and he got his PhD. He became a doctor at 18. He was in advanced mathematics. He was a child prodigy. It's very difficult to become a full professor at a university. He was a full tenured professor by the time he was 20. That's how amazingly bright this guy was. Yeah.
He was Scotland's answer to Gauss, right? I suppose.
Oh, well, since Gauss is a German, I'd rather you. Well, I think Gauss was German. Yeah, I think he was. I'd rather you compare him against something else. Germans and British have problems when it comes to the fact that Leibniz is a thief and stole calculus. So Germans have a bad reputation, in my opinion. What do I know? Okay, let's tell you what Maclaurin's found out. He found out that if you wanted to find the power series of any function, you use this formula. Now, the only piece of that that's probably got you a little confused is what on earth is that? Well, it's the nth derivative. So it's, when that's 5, it's the 5th derivative, right? When that n in the brackets is 20, it's the 20th derivative. So it's the nth derivative evaluated at x equals 0. So we are going to pretend for a minute that Maclaurin, who discovered this first, was playing about with things, and he discovered the following rather amazing fact. So he done that, and then he found its first derivative, and he found out, oh, well, that's nice. Isn't the first derivative of e to the x, x? And isn't the second derivative e to the x? Well, do you know that the notation that we use for derivatives is Roman numerals? Right, so if I wanted to do the 5th derivative, we would get that, right? Although I don't think you would probably do that. Can you see that that notation gets quite cumbersome if you want to do the 139th derivative? Nobody's going to use Roman numerals. So we created this notation. The 101st derivative with a little bracket around it. Do you see that's quite, it kind of makes life easy. So does that now make more sense when you see it? Right. Now, what is this guy at 0? Well, he's e to the 0, which is 1. But wait a minute, isn't everybody 1? Agreed? So what would the nth derivative at 0 be? Where n could be any derivative, right? The 101st or the 2 billionth and 1. Would you agree it'd be 1? The nth derivative of this function evaluated at 0 would be e to the 0, and e to the 0 would be 1. Agreed? That means that e to the x can be written as n equals 0 to infinity, the nth derivative at 0, x to the n over n factorial. Well, if that's 1, it means the power series for e to the x is that guy. And if you want to see what that guy looks like, isn't there something really symmetric and elegant about e to the x? Oh, and a side note, e to the 0 is 1. 0 factorial is 1, right? It is, because it is. That means, haven't we got a power series for e to the x now? Oh, come on, that is cool. E to the power of x can be written as this infinite polynomial. Right, let's try some. Isn't e to the 1? Agreed? Anybody know what e is off the top of their head?
Approximately 2.71.
Okay. If I use just the first 4 terms, right, that's my going rate, and a little bit of calculator, shouldn't I be able to come up with what e looks like? Well, let's see. It's going to be 1 plus 1 over 1 plus 1 squared over 2 factorial, which is just 2, plus 1 over 3 factorial, which is 6. And the answer I get is 2.666. Oh, not quite there. What do you think I need to do then? I want a better answer. Going to just add another term. If it's not good, add 10 more terms. Could you imagine writing a program just to add this up? Could you imagine, you know, for I equals 1 to a million or something? Wouldn't it be pretty easy to do? Previous term plus 1 more, previous answer plus 1 more term. Pretty cool. I think so. Well, that's e to the x. So I'm going to put that guy in my little I now know who you are list. And I would like to know the power series of e to the x squared. And I don't want to do that derivative thing. If I know this, can't I get that? And the key here is substitution. Won't I replace this x with x squared? And so n equals 0 to infinity, x squared to the n over n factorial. I now have and let's suppose I want to integrate that guy. Do you know how to integrate analytically? In other words, exactly, e to the x squared. Or does that count as one of the many we don't know how to do it guys?
That's a bad guy.
That's a bad guy. But isn't that bad guy now simply going to be, as a power series, that guy? And that I can do by adding 1 to the power, dividing by that new power. Technically plus c, right? But that would be true anyway, wouldn't it? You see, we've got a very powerful analytic tool now. If I have a function and I can find a pattern in its nth derivative, then I can generate a power series for it. And if I can generate a power series from it, can't I use that power series to generate lots and lots of other power series? Couldn't I do x to the x? In fact, wouldn't that be simply x times this answer, which would give me a power series? See how easy it is to play? Just give me something to work with, and then you can go running. Can't you do all sorts of, oh God, you could keep going forever, right? I mean, there's no limit. Can I don't know, make that x cubed? Can I make that e to the x to the 4 and do a power series by just some substitution tricks? So we don't typically find, using Maclaurin series, power series. They're very difficult to do from scratch. E to the x is a very nice one, right? A lot of the time, they are not that easy to do. And what we tend to do is we tend to just find the power series for a few very important functions. E to the x, sine x, cosine x. We put in the effort and we get them. But once we get them, can't we just play about with substitution for all the other guys? We don't do everybody. We don't reinvent the wheel every time I want to get the power series or something. Because aren't most things built up from those guys? X sine x, e to the x cubed, you know, things like that. Now, if the function is horrendously scary, I know, like e to the power of sine x, forget it. You know, there are limitations to everything. I don't think anybody could do a power series of that function. We know theoretically it exists, but we wouldn't be able to generate a pattern, I'm pretty sure. So if e to the x is this guy, wouldn't it be nice to see the power series for cosine x and then for sine x? Wouldn't you like to see those? No? Yeah. There you go. Cosine x is made up of this. Sine x is made up of this. I'm just telling you they are, but if you had time and patience, couldn't you find the derivative of sine x, find its first, find its second, find its third, find its fourth, do it as many times as you need, evaluate all those derivatives at 0, and then look for a pattern. And the pattern that you need to find is what that guy is equal to in terms of n. And then you can stick it inside Maclaurin's formula, basically inside there. And you might think, why is that 2n and why is that 2n plus 1? Seems a reasonable question to ask. When you do a sine function, for instance, don't half the time you get a version of cosine. Do you know when you evaluate them at 0, don't half the terms disappear and the other half get you 1 or -1? So that's why these get generated the way they did. It's basically to do with the fact that half the terms are missing. Let's take sin x. If you plug in 0, you get x. Then you get take away x cubed over 3 factorial. And then you get add x to the 5 over 5 factorial. And then you go like that. Last time e to the x didn't do a very good job, and I had to use 4 terms. And what the right answer is 2.7128, and I got a lot of 6s. Right, it wasn't great. It was getting there, but it would take a while. Do you think this one's going to do a better job? And I'm only going to use 3 terms. Okay, let's find out. 0.1234. Take away 0.1234 raised to the power of 3 divided by 3 factorial, which is 6, plus 0.1234 raised to the power of 5 divided by 5 factorial, which is 120. And the answer I got was 0.123087 and some stuff. And according to the calculator, the sign of 0.1234 is 0.123087. Oh, okay. 05830582. Come on, be impressed. A 3-term polynomial is giving you the value of this sign to 1, 2, 3, 4, 5, 6, 7, 8, 9. And who's to say that that's not been rounded off? Could not be correct even to that decimal place. So those poor guys that were doing the calculations that, you know, our student earlier was mentioning, can you imagine that they would just have power series and they would be doing some really horrendous powers, right? But doable, right? And they could come back and give the guy the answer to 8, 9, 10 decimal places. And that guy would be, if it was me, I'd be suitably impressed. Can you tell that I like power series? I'm amazed, still today, and probably will be for the rest of my life, how this guy Maclaurin even thought of that. I mean, try and have a mindset where there's a thing called sin x, right? Sin x does that. And he had the insight. I wonder if that guy is an infinite polynomial. And then, how do I find out this formula? How do I construct it? Where does it come from? How on earth did he come up with it?